Dear colleagues, let me see to start this session. I'm glad to see you in this conference and this session. First talk, invited talk from Professor Mr. Michael Buldakov. And please take a look this reglement. Invited speech 30 minutes and other oral speech 20 minutes. Okay. Let's start this first talk. Майкл Булдаков, please. Иван, а почему я не слышу?
Dear colleagues, do you hear me?
Oh.
Okay, can you hear me?
Yes.
Can you hear me? Is it okay? Can I start? Okay, thank you very much. Okay, dear colleagues, I'm glad to hear you and see you. So I want to present to you the result of almost 20 years experiments between three Tomsk institutes. And as I am an oncologist, I will focus on the result of the medical experiments, and I'll try to show you how does the equipment which you are created can be used, for example, in medicine. First, I want to say why did we start experiments with pulsed X-ray? About 20 years ago, we read a lot of paper about situation with the pulse regime of different type of radiation, like microwave, ultrasound, and other radiation. And the main idea was that pulse repetition frequency can strongly change the reaction of the biological objects. But at the time, there were no data about the pulsed X-ray radiation. So we decided, what if we can change the traditional continuous radiation with, say it, very long pulse, one pulse with low dose per pulse, and we, what will be if we change it to the radiation with very short pulses, up to few nanoseconds, and increase the dose per pulse. So for me, like for oncologists and for biologists, was important that pulse duration should be just a few nanoseconds, and dose per pulse you can hear there. So we decided to try to use the pulsed X-ray radiation in the medical researches, because of course the first question, if you ask where we can use the X-ray machine, the first is cancer treatment of oncological patients. So we decided to solve one of the main problem of the oncology. You all know that to kill cancer cells, we have to use very high doses, up to 20 and 90 gray. Because of doses less than 1 gray, cannot kill the tumor cells. And these doses are not efficacy. But the problem, of course, is the side effects of such big doses. So we decided, what if we will use the pulse X-ray radiation? Could we keep the efficacy of low doses, doses lower than 1 gray? So we tried to solve the problem of side effects. So what did we do first? First, of course, we complete some experiments with the tumor cells line, not with the animals, but first with the line. So what we got first? Here you can see the graph with cell proliferation. Cell proliferation means cell growth. Low cell proliferation means that almost cells are dead. So we use pulsed X-ray radiation and irradiated. Here you can see from 1 up to 7 different types of tumor cells, and all types of tumor cells, almost up to 95% were dead. And the first very important, here you can see the picture. This is the control group. There are a lot of colonies of cells, and here you can see by the microscope, and even just by your eyes, you can see very small number of tumor cell colonies. What is the first main point of that experiment? That we use the dose, total absorbed dose, 0.003 and up to 0.06 gray. So the total dose was only 60 milligray. But if you want to get the same effect with application just regular radiation, non-pulsed radiation, you have to use the dose more than 2 gray. That was the first very interesting fact. The second fact was, if you look at this part of the graph, you can see the cell number 8. This is not tumor cell. This is a normal, just normal cells. And you can see that we did not kill the normal cells. And that was the second very important point of our first investigations, that we can kill the tumor cells, but we didn't kill normal cells at these small doses. The next point was how did the parameters of the pulse repetition frequency can change the reaction of biological of tumor cells and normal cells. So we used one cell line and we irradiated cells with a different pulse repetition frequency. This is the control. And here you can see that, for example, pulse repetition frequency 10, 13, and 16 Hertz almost kill all the cells. But at the same time, if we will use the pulse repetition frequency, for example, 29 Hertz, we didn't observe any reaction of the tumor cells on the radiation. And at the same time, if we use 22 Hertz, we can even stimulate tumor cell proliferation. So the second very important goal was that pulse repetition frequency of pulse X-ray radiation is very, very important to reach the effects which we really need. Of course, the main question at that time was why the pulse repetition frequency is so important, why 10 Hertz is more effective than 22 Hertz, for example. We tried to understand it, and we investigated intracellular processes in the tumor cells. We observed increase of reoxygen oxygen species. We observed changing in mitochondrial membrane potential of the cells. We observed difference in the type of cell death. I don't want to give a lot of details because it's a very it's a strong biological specificity. But at that time, we still cannot answer why one pulses are more effective, for example, 13 Hertz, but 22 Hertz, for example, are not so effective. We still don't know it, but we checked it for all for all type of tumor cells, and these 3 pulse repetition frequency still more effective. So at this part, we could conclude that pulse repetition frequency are very important. And the second, that we can kill the tumor cells even if we use the dose less than 1 gray. And that after that, we started experiments with the animals, with the model of tumor. We call it in oncology, we call it metastatic Lewis lung carcinoma. This tumor grows in the limb of mice and gives metastasis to the lung. So what did we get? So what did we get? We completed a lot of experiments with the mice. We changed pulse repetition frequency. We changed dose rate. We changed dose per pulse. We changed fraction of number of fractions. We did a lot of experiments, and finally we've got a few regions where we can get the very good results, and I'll show it now. This is the picture how the mice were irradiated. It was they were covered with a lead box to protect the body, the brain, and the other organs, and we irradiated only the limb, right back limb, with the tumor. So what did we got? Here you can see the main results of our investigations. On this picture you can see the growth of tumor of mice. The blue color is the control group, and red color you can see the irradiated group. And this is the days after transplantation of the tumor to the mice. You can see that effect, and we used 5 fractions by 40 milligray, so total absorbed dose was 0.2 gray. And what is very, very important, as it was in experiments with the cell lines, if you want to get the same effect with the traditional non-pulsed X-ray, you have to use doses up to 40 gray. So once more, we used 200 milligray, and for traditional X-ray non-pulsed, you have to use 40 gray. It's 200 times higher. This is very, very important result. But the most important result was that we observed inhibition of lung metastasis in mouse up to 60%. Why this result is more important? Because metastasis is the main reason for death of oncological patients. Because primary tumor you can cut by surgery, but if some cells still in the organism, they will go to the organs and gives new colonies, and patient will die. So inhibition of metastasis is the most important result with using low dose pulsed X-ray. After that, we did one more experiment, very interesting experiment. Later you will understand why I'm going to talk about this experiment. We lead the mice, we protect the mice with the lead box, and we also protect the leg with the tumor, and we irradiated only health leg. So once more, we protect the leg with the tumor and irradiated only the health leg. What did we observe? Of course, we didn't find any statistical difference in tumor size because the primary tumor was covered. But we still observed inhibition of lung metastasis, even we irradiated the health leg. What did we suppose? We supposed that pulsed X-ray could not only kill the tumor cells directly, but also stimulate function of the organism. For example, like immune function. And actually, there are a lot of publications that low doses, just regular low doses of X-ray, not pulse X-ray, really could stimulate the immune function of the mice through the activation of macrophages. So we checked if the pulse X-ray also can do that. Macrophages is the cells which can produce in our organism, which can produce the special mediators. I don't want to talk a lot about this, about the mechanism of macrophages, because it's strongly biology. But what I want to say, that macrophages can produce some cytokines, and here you can see that irradiation with different pulse repetition rates and different doses, total doses, can change the secretion of cytokines by these cells. So that means that X-ray can stimulate the macrophages. The second was that if we will irradiate the macrophages and add these cells to the tumor cells, they will also kill the tumor cells, just macrophages. And the last very short information also about the immune function of organism and macrophages. That macrophages, actually, we have two types of macrophages. One of them are good for tumor, but one of them are bad. And we checked if our pulsed, low-dose pulsed X-ray radiation can change the phenotype of the macrophage from this to this. Here on the picture, on the photo, you can see the fluorescent photography of the macrophages, of the cells. Green means the macrophages first type, and if we can see the red color, it means that it changed to the another phenotype. So this results means that really we can irradiate macrophages with the pulsed X-ray and induce their function, and they will protect the organism from the tumor. So summary, what we can conclude. We can conclude first that repetitively pulsed X-ray can kill the tumor cells even at the doses less than 1 gray, in vitro or in vivo, doesn't matter. The second, that effects strongly depend on pulse repetition frequency. And the third is that pulse repetition, that pulse X-ray can stimulate function of immune system of organism. So this is the last slide, and that's how I want to show you how does the technique what you are created like a physician can be used in medicine and can open the real perspective for its application in future. Thank you for your attention, and if you have a question, I can answer.
Okay, thank you very much for your talk. It's very interesting lecture. Dear colleagues, questions, please. Michael, I have a question to you. What is, remind us the energy of X-ray or accelerating voltage for this accelerator?
As I remember, it's 117 electron volt. Yes, as I remember.
Mm-hmm. Okay, thank you very much.
Mm-hmm.
Michael, another question. Do you see the question?
Yes, I see the question. Did I try to apply radiation with 22 Hertz to healthy cells? Yes, of course. When we did the experiments with the normal cells, we also checked all pulse repetition rate, and we also observed that depend on pulse repetition rate, we can stimulate or didn't observe any effect on normal cells. So the main thing is that changing this parameter, we always can find the regime, always can find the pulse repetition frequency where we can kill the tumor cells and did not kill the normal cells. Can you repeat once again? The mice had tumor in the lung, but you treated it and still so. Yes, yes, that's correct. The third part of our experiments to check the influence X-ray on immune function was the experiments when we protect the tumor in the leg and irradiated only health leg. These experiments were made only to check if we can stimulate the immune function of organism. Yes, and we observed the inhibition of metastasis in lung, not in primary tumor, only in lung. Yes, that's correct.
Okay. Another question, please. Ivan Kurkan.
I mean, that might be used as some kind of stimulator out of cancer. Yes, probably it could be used for like a stimulator of immune function of health people or of health mice. Of health mice, of course, experimental researchers. Yes, it could be, but maybe it's not so good to use X-ray just for stimulated immune function, because we have a lot of chemical stimulators of immune function. But if we apply it for cancer treatment, this is, of course, better, because we can use the double function of pulsed X-ray, killing the tumor cells and stimulating the immune function.
Okay, thank you. Another question, please. Okay. No questions.
Okay, thank you very much.
Okay, thank you very much, Michael, for very good talk. Thank you. Okay. Dear colleagues, next talk from Professor Grigory Argunov from High Current Electronic Institute. Grigory.
Меня слышно? Меня слышно?
Grigory, please.
Hello, everyone. In my presentation called cathode thyratron triggering in the electric circuit with grounded cathode and grid. In this work, I will present an upgraded cold cathode thyratron with a new trigger unit, and will demonstrate how it works in a new electric circuit where cathode and grid are grounded. And first of all, let's talk about the application. Cold cathode thyratrons find wide variety of applications due to fast switching capabilities. They include medicine, various power generators, ranging from laser pumping to generators for particle accelerators, and of course many other applications where fast switching capabilities are needed. There's a common issue associated with providing nanosecond triggering stability in commercially produced devices. The systems where a large number of switches operate onto a common load require low jitter. One of the examples is a linear accelerator, LEA20, with it includes 48 modulators where 96 cold cathode thyratrons operate simultaneously. And of course, it's crucial to provide very low jitter here in such systems. In case of commercially produced thyratrons, the trigger units based on auxiliary glow discharge. The device and the electric circuit for triggering is on the left side of the slide. This device has a trigger unit based on an auxiliary glow discharge. The auxiliary discharge sustained in this cavity of the electrode C1. The auxiliary discharge provides pre-ionization inside the trigger unit in order to facilitate development of the trigger discharge. Here the device connected in the electric circuit for discharging the capacitance CO to the resistive load. The main discharge gap includes the electrode A, the electrode C, and a gradient electrode G between them. Pressure of the working gas in the device adjusted by a hydrogen generator when we apply a voltage to this generator. The main discharge cap connected to the cathode cavity C through the holes in the upper part of the electrode C. When triggering, a high current pulse discharge ignites between the electrodes A and C. In commercially produced thyratrons, jitter depends on the sustaining mode of the auxiliary discharge, sustaining between the electrode A1 and C1 by means of the power supply VA. The so-called high emissive tablet connected to the cathode C1 used in order to initiate the discharge at a low voltage. However, the tablet makes the auxiliary discharge unstable, meaning that spontaneous transitions from one of the mode of the discharge to another are occurring. It can be seen from these waveforms. When we apply the trigger pulse, the green curves. Each time the trigger discharge may spontaneously ignite in different modes, causing quite a huge jitter when the device operates. And it's all due to the high emissive tablet used here, because once we applied the trigger pulse, the auxiliary discharge, it affects the tablet, and the auxiliary discharge changes its mode. It may be changed spontaneously, which is seen from the waveforms. And in order to resolve the issue, an upgraded thyratron with a new trigger unit was designed. It's all to get away from the emissive tablet. The main gap electrodes left unchanged. They are the same as in commercially produced devices, but the trigger unit electrodes designed as whole cylinders here. The thyratron switches the capacitance CO onto the resistive load. The auxiliary glow discharge with current of 20 milliamperes sustains in a trigger unit before triggering. The main fraction, it's sustained by means of this power supply. The main fraction of this current flows between these electrodes, between A1 and C1, and measured by this shunt. And there's also a small fraction of the auxiliary discharge current flowing through the hole in this area onto the electrode C, and this fraction called a parasitic current. Applying the trigger pulse causes trigger discharge initiation in the trigger unit. The discharge current flows to the cavity C1 and to the cathode cavity C through this hole. As the trigger pulse is negative, the whole anode plasma is generated inside the cavities C1 and C, and the electrons from this plasma extracted into the main gap through these holes, and the breakdown of the main gap occurs, discharging this capacitance. Before triggering the device in the presence of anode voltage, let's consider development of the breakdown in the trigger unit. Here are the experimental waveforms of the voltage VA1 measured at this point, and the currents E1 and E2 measured by these shunts. And here is the experimental arrangement of the experiment. Before applying the trigger pulse, the auxiliary discharge with current of 20 milliamperes was sustained. and the parasitic current was 0.3 milliamperes. The auxiliary discharge modes here corresponds to the ordinary glow discharge with a negative glow plasma in the cavity of the electrode C1, and positive calmed plasma inside the electrode A1. Applying the trigger pulse changes polarity of the electrode A1, it becomes negative and turns into a hollow cathode. The voltage of the electrode A1, the point TO is the point when the trigger pulse was applied. The voltage of the electrode A1 rises, and by the point T1 we see a sharp voltage fall. This point corresponds to a rising of a pulse discharge in the trigger unit. It can be seen from the waveforms of the currents. The interval from here to here is the delayed time to break down in the trigger unit. The current E1 appears before the point T1 during the voltage rise, this stage. Most probably, the current at this stage is displacement current. After the point T1, the discharge current E1 rises sharply. It reaches 32 amperes. The further decrease of the current associated with discharging the capacitor in the trigger pulse generator. Concurrently with the current E1, the current E2 begins to rise and reaches 2 amperes. So this current measured by this shunt. This current, it flows through this hole to the cavity C. Ideally, the current E1 of the trigger discharge should be completely intercepted to the electrode C in the course of triggering. In the condition presented here, only certain fraction of the pulse discharge intercepted, quite a small fraction. However, as it will be shown later, this fraction suffices to trigger the device. Here are the waveforms illustrating breakdown in the main gap. And this is the experimental arrangement demonstrating how the device is triggered in the presence of high voltage at the anode. VA is the anode voltage measured here. ER is the anode current measured in this circuit, and VA1 is the trigger pulse applied to the electrode A1 measured here. Like in the previous experiments, the electrode A1 has positive potential due to the auxiliary glow discharge before applying the trigger pulse. In order to trigger the device, the trigger discharge plasma has to be generated in this cavity. This plasma appears after breakdown in the trigger unit when the current onto the electrode C appears. This process was considered on the previous slide. The electrons from the plasma inside this cavity extracted into the main gap via these holes, so that the main discharge initiates. We can point out the delay time between the breakdown in the trigger unit, this point, T1, and the point when the current in the main discharge gap begins to rise. This interval amounts 58 nanoseconds, and this is the delay time to breakdown of the main gap since the trigger discharge occurred here. The total delay time to triggering is the sum of the delay time in the trigger unit, this point, and between this point. It amounts 108 nanoseconds, and jitter here does not exceed 4 nanoseconds. One of the problems of the thyratrons is to achieve low jitter for a wide range of gas pressure. The gas pressure inside the thyratron adjusted by the voltage of the hydrogen generator. On the left graph, we see how the breakdown voltage depends on the gas pressure. Here is the voltage on the hydrogen generator, which corresponds to the gas pressure. The dashed line shows what was measured, as we couldn't increase voltage higher than 55 kilovolts, but the solid line shows real dependence. The breakdown voltage amounts 44 kilovolts at voltage of 5.7 volts on the generator. However, further increase of pressure, moving rightward to that side, leads into sharp decrease of the breakdown voltage to less than 30 kilovolts. The data on triggering characteristics depending on gas pressure is on the right graph. In terms of triggering characteristics, it's better to operate at highest possible pressures. As we see, at quite low pressure, the delay time is 140 nanoseconds and jitter is about 8 nanoseconds. But at this point, at high pressure, the delay time is 108 nanoseconds and quite low jitter of 4 nanoseconds. It's better to operate at the highest possible pressure. However, the upper limit of the operating gas pressure determined by the operating anode voltage. In other words, we can't set the hydrogen voltage higher than 5.7 volts if we operate at anode voltage higher than 44 kilovolts. Otherwise, the main gap breakdown will occur. The experimental results on triggering an upgraded sealed-off cold cathode thyratron with a new trigger unit based on auxiliary cold discharge have been presented in this work. The simple electric circuit for triggering an upgraded thyratron has been proposed. The essence of the proposed electric circuit is that the cavity of one of the trigger unit electrodes is connected with the main grounded cathode. And with the usage of this circuit, the conventionally accepted design of the thyratron can be simplified. For example, making the cathode and the grid as a whole. The experimental data shows that in typical operating mode, the delay time to break down amounts 108 nanoseconds, and jitter does not exceed 4 nanoseconds. And that's all. Now time for questions.
Okay. Thank you very much for your talk, dear colleague. Questions, please.
I see a question from Ivan Yegorov. What is the time delay between peak of voltage and current signal in the page 6? How to reduce the meaning? 1 minute. You mean what is the time between this point and the what current signal? Well, when we applied the trigger pulse, it was 50 nanoseconds till the I see till the point T1 when the currents began to rise. Then this peak is when the time from this point is 75 nanoseconds. So the time between this peak and this peak is about 25 nanoseconds. And how to reduce the delay? Well, one of the ways is to apply voltage with a shorter rise time. Yeah.
Okay. Ivan Yegorov. Okay. Another questions, please. No questions. Okay. Grigory, thank you very much for your good talk. It's very nice device. Okay, thanks
Thank you
again.
for your patience, for your attention.
Okay, dear colleagues, another talk. Evgeny Petrenko. Evgeny.
Hello, 1, 2, 3. You hear me?
1 minute, please. Okay.
Do you hear me?
Yes, we can
Evgeny,
hear you.
please.
Okay. So, good afternoon, dear audience. My name is Evgeny. I'm from Tomsk Polytechnic University. And as you can see,
Евгений, громче, пожалуйста.
is it better?
Yeah.
Okay. So, as you can see, my topic is synchronization of two pulse voltage generators with different polarity. So, first of all, I would start with a short kind of introduction just to explain how we came to this idea of synchronization two pulse generators with different polarity. So the relevance of the study is increasing need for destruction and disposal of strong concrete and reinforced concrete structures and structures during repair, dismantling and disposal during decommission of buildings. Also drilling of thermal wells and especially drilling in permafrost. Despite significant progress of traditional methods for destruction, the destruction performance remains generally very low, and the cost is high. The main reasons for this are firstly, rapid wear out of destructive tool, difficulties of transferring sufficient energy to the phase, and low destruction efficiency. So given this, along with improvement of engineering and technology based on mechanical methods of destruction, a searching of new methods of destruction based on modern achievements of science and technology are being conducted. And one such destruction method is electric discharge method, where the destruction tool is plasma. So here, figure 1 shows an illustration of the main idea of this method. Implementation of electric discharge technologies is carried out by creating conditions for development of discharge through a solid dielectric. As we can see, with decreasing exposure time, the strength of liquid dielectrics becomes higher than the strength of solid dielectrics. And this leads to the fact that when pulses with front less than 1 microsecond are exposed, the discharge will pass through solid dielectric and destroy it. So previous experiments have proven pretty high efficiency of electric discharge technology, but industrial application is still limited because of low reliability of high voltage pulse equipment because of high voltages around of 400 to 800 kilovolts and high insulation requirements. So one of solutions of these problems can be using bipolar method. Here you can see electrical scheme of the installation, which consists of two platform type generators assembled according to Arkadyev-Mark scheme. Both of them consist of 5 stages with capacitors. Capacitors are charged through inductors. One side charged by positive polarity and another side by negative. Each generator must provide output voltage with amplitude around 150 kilovolts with pulse front duration less than 1 microsecond. This requirement for the duration is formed according to empirical law that I just explained earlier. It needs just for possibility of penetration the discharge through a solid dielectric. So triggering is carried out by using triggertrons here, which in turn are triggered by 2 pulse generators, which marked here as the starters. So to fine-tune the synchronous start of 2 pulse voltage generators, the control signal for the pulse generators comes via optical channels with adjustable delay of 2 microseconds. So what else? Ball gaps are made of stainless steel and located in dielectric tube. It looks like this here. You can see appearance of the installation. In foreground you can see 2 generators and in background discharge chamber. Operating voltage of pulse voltage generator was regulated by changing distance of interelectrode gaps of the balls at each stage. Well, next, here you can see a measurement system. Voltage pulses were registered by using pulse voltage dividers, ohmic voltage dividers, and for the highest accuracy, the measuring system was calibrated by including matching elements, and everything was built according to recommendations of literary sources. The voltage signals were recorded by using digital oscilloscope tektronix. On this slide are presented oscillograms for experiments of idling and for short circuit as well. Here we have 2 curves. Black curve is a positive polarity and red one is a negative polarity. You can see that discharge of 2 generators occurs pretty simultaneously, but at the same time we can see that there is a little delay in this oscillogram. So it happens due to inaccuracy of elements. You know that nothing is perfect. I mean elements, but anyway, as I already said, we can regulate the delay, and the accuracy of synchronization varies within tens of nanoseconds. And as a result, we got successful tests of synchronization system allowing to change the delay. This method reduces chance of unwanted breakdown between high voltage electrodes and grounded parts of the installation, reduction of electromagnetic interference to the external network. And the last one point is quite good and important achievement for electric discharge technology in general. So is that the total breakdown voltage with simultaneous action of 2 different polarity pulses is less than under influence of unipolar pulses. So yeah, it's already more another topic for another report, but anyway, I decided to notice it. So that's all. Thank you for your attention.
Thank you very much, Evgeny. Dear colleagues, questions, please. Okay.
Yeah, I see. Question: is it possible to ground one of the electrodes? So the let me see. Actually, it's possible, but it's no need for this method. The main idea of this method is have no to grounded electrodes. They both are potential with different polarities.
Is it all? Evgeny, next question.
Oh, yes, next question. How do you reduce MI?
Do you see question?
Yeah, I see. Honestly, it wasn't measure. Sorry, let me think.
Do you understood question?
I think so.
Okay, please.
But okay, maybe I can answer. Maybe I can answer by email or private because now I have some problems.
Maybe.
Is it okay, Ivan Kurkan?
Ivan Kurkan has another question.
Where I can see?
It was stated in conclusion.
Yeah, he's. Yeah, I see. He said.
Reduce of electromagnetic.
I said. Yeah, I understood. So he said that I can see in the forum, and then I'll give him response.
Okay.
Another questions?
Another question, please, and communicate with Ivan after your talk, man. Ivan Yegorov question, do you see this question? Evgeny.
Yes.
Question from Ivan Yegorov. Do you see this question?
The second question or the first one? I answered already.
Oh, yes. Okay. Dear colleague, another questions? No question. Okay. Thank you very much, Evgeny.
Thank you.
Another talk from Professor Victor Paperny. Виктор Львович, вы слышите? Вы здесь? Окей. Окей. please.
Скажите, что please press the green button, чтобы выйти в эфир.
Ну, Виктор,
Please press the green button go on air. Наверху зеленая кнопка.
oh. Okay, I see you, Виктор Львович.
Алло, Геннадий Ефимович, слышно меня?
Слышно, но лучше, если громче.
Сейчас слышно меня?
Yes, we see you and it's very good.
May I start my presentation? Yes?
Yes, yes, we see.
Okay.
Please
Good day.
continue.
Powerful wide band, VUV and UV radiation. This work was carried out in the Irkutsk State University this year, and now I start my presentation. Okay. The next slide. How can I commutate this slide?
Ivan, help us.
Yes.
Okay.
Yes. I see. Okay.
Виктор Львович, Иван будет переключать слайды, если это можно.
Okay. This is a review of our accelerator, small-sized accelerator. You can see that its dimensions are small enough, and here we present the parameters, principal parameters of the accelerator. You can see that voltage is about 300 kV,
Yes.
5 kiloamps is the average current of the discharge, and 200 picosecond is the length of the pulse. The rate of the current is about 5 times 10 to 13 amps per second. The next, please. Okay. Now let's try to formulate the problem of our study. The first problem is to study this parameter of the VUV and UV plasma radiation from this high voltage discharge at atmospheric pressure xenon with the modified design of the electrode array. And the second problem is comparison of the radiative characteristics of this discharge and the atmospheric pressure discharge sustained by the well-known radon 220 nanosecond high voltage facility from the High Current Electron Institute. Okay. Now let's consider briefly the design of our accelerator and the discharge chamber. Here are the principal parameters of the pulse. That's the length, current, voltage, repetition rate, and input discharge energy was small enough, about 0.3 joules. And that's our detector. That is pin diode with this parameter. And the typical discharge pulse, voltage of the discharge, is presented at this panel. We can see that length of the pulse, full length and half magnitude is 200 picosecond, and amplitude is about 300 kV. Compare this design with the design of the radon 220 accelerator. Here we can see the difference between design of the discharge chamber. We use a hemispherical cathode manufactured from brass, and in radon accelerated usually uses a tubular cathode with thin walls and a plain anode. We have a conical anode as presented at this panel. Okay, and typical waveforms of the discharge voltage and current of the radon accelerated are presented here. We can see that length of the typical length of the pulse is about 2 nanosecond. Here the paper from which we took this data. Okay. Here we present the image of the end view of the discharge in two modes of the discharge. In the volume mode, the left photo, and so-called streamer mode, right photo. Both photos were made in the UV spectral range presented here by a special camera. We can see here that in the volume mode of the discharge, the plasma is, the discharge has a diffuse form. No peculiarity are observed here, unlike the streamer discharge, where these bright streamer are observed. Let's compare our photos with that of the radon accelerator discharge sustained by the radon accelerator. We can see here the diffuse. That's also the volume mode, but we can observe here jets that are diffuse jets, and this mode, author of the paper suppose that it's diffuse mode of the discharge. Nevertheless, the diffuse jets are absorbed here. That's different. That's this form differ from our discharge. Now let's consider in detail the signals of our from our discharge of the pin diode, and in two modes. That is our volume mode, and that is streamer mode. And here the waveforms of the discharge both discharge current pulse and radiation intensity at a wavelength of 140 and 72 nanometers. We can see here that significant differences between all these waveforms. Waveforms of our discharge in volume mode is presented here, and we can see that length of the discharge is about 1 nanosecond, is less than 1 nanosecond, because the resolution in time of our oscilloscope is no less than 1 nanosecond. About the streamer mode, we can see that length of the pulse is rather more, and about 50 nanosecond, and amplitude of this signal is significantly less, about 3 orders of magnitude is less than this in this mode. And radon radiation from the from the discharge sustained by the radon is length of the pulse is rather more than in our case, and it depends the length, both lengths and the amplitude of the signal depend. Both these values depend on the pressure of the working gas. That is the signal at this pressure, that is signal at this pressure. This signal is amplified by 10 times, and that means that a significant dependence on the pressure of the working gas is observed. Unlike this result, in our case, we didn't observe any significant dependence of the signal from the pin diode within a wide range of the pressure variation. We can see here that both signals signals in the full spectral range sensitivity of the diode, and through UV filter in the ultraviolet range, spectral range. We can see here significant difference both in the lengths and in the pressure of the working gas between our result and result obtained early in this discharge. I should note that there is other works other than this work, where the author of this work have shown that with the enhancement of the pressure of the working gas, both the amplitude and the length of the signal change significantly, namely the intensity of the radiation increased significantly, and length of the radiation pulse decreased significantly also. Now let's compare characteristics of the radiation obtained in our discharge and in radon, discharge sustained by radon. And now let's compare the spectral characteristics. We can observe here that the spectrum, the observed spectrum of xenon in this experiment is observed as the form of this spectrum is a band with maximum at 172 nanometers, and the width of this band is about 20 nanometers. Unlike this result, in our case, we observe the spectrum as a continuum in UV spectral range, in the volume discharge mode, and unlike this mode, at the streamer discharge mode, we can observe the spectrum as a bell shape, and intensity of this spectrum is rather less than in the volume discharge mode. This shape of the spectrum shows that the main part of the spectrum lies in this range, spectral range, in more in short wave range, and then we suppose that this spectrum can be fitted by a Planck distribution. Okay, the next, please. Okay, that is our spectrum. That is the experimental spectrum. We can distinguish here three ranges. The first range, this range, long wavelength range, correspond to spectrum range recorded through UV filter. This part of the spectrum lies in the UV spectral range. This range corresponds to recorded VUV range, and since this experimental spectrum can be fitted with good agreement by the exponential curve, we suppose that we can fit the whole full spectrum by the Planck distribution. It is presented by the dotted curve, and maximum of this spectrum lies at 30 nanometers. It corresponds to radiation temperature of the emitting gas, about 10 eV. It should be noted that the similar results were obtained both in xenon, in nitrogen, and argon. Now, to try to summarize our results. This table presents a sum of the results and comparison with the data obtained from the Radan facility. This is the difference in the electrode array design. This difference in the length of the pulse. That is difference in the input energy in the discharge. The energy is less in our case, about 3 times compared to Radan accelerator. That is the length of the pulse of the radiation pulse. That is parameter of the radiation. This parameter of the discharge. We can see that length of the pulse in our case is about an order of magnitude less than in the Radan facility, but the later results from this accelerator showed that the length can be decreased about an order of magnitude. Nevertheless, it stays, the length stays about the order less than, about an order more than in our case. About here, about 10 nanosecond, and here about 1, less than 1 nanosecond. And therefore, the peak radiation power in our case is about an order of magnitude more than in this case. Full radiation energy is less in our case, and the fundamental difference is the significant difference in the shape of the spectrum. Here is the band, as I said above, and here the presumably surely Planck distribution with this parameter. That is the band, that's the range, spectral range, and the maximum position of maximum. That's the that corresponds this this spectrum corresponds to this temperature. Okay, so I complete my my presentation, and thank you for your attention.
Okay. Thank you very much for your talk. Questions, please.
Volume of the what was okay. What pulse repetition rate is available for described regimes? The maximum repetition rate is 12 pulse per second. And what the volume of the discharge chamber? About 3 cubic centimeters.
3 cubic centimeters.
Cubic centimeters, yeah. How did you measure pulse duration of 200 picosecond? By means of the oscilloscope TDS 62404, as I remember. And a special divider, two-stage divider, high voltage, matched dividers. The capacitive divider, the first stage, and the special coaxial divider, the second stage. That's a very difficult problem. You are right. This question is good.
Okay.
This limitation, there is no principal limitation. This repetition rate is limited only by the power of the source, power supply. We can increase this repetition rate, but it wasn't our problem, our task currently.
Okay. Okay. Another questions, please? No questions. Okay. Okay. That's all. Victor, thank you very much again for your talk. See you.
What is commutation?
Another talk. Next talk from Maxim Lavruhin. Maxim, do you see? Do you hear?
Yes, hello.
Okay, 1 minute. Okay, please.
Hello. Yes, hello, dear colleagues. I would like to present our work dedicated to investigation of the output characteristics of the lasers on self-terminating transitions of metal lines pumped by a high voltage generator, which is based on the new type of the switch, which was called Vector. Particularly, I will talk about the study of barium and mercury vapor lasers. The oscillation in a self-terminating laser is a transition by virtue of either failure or sustained excitation of the upper laser level or to clear the lower laser level with continued pumping. Self-terminating lasers are therefore, for their nature, pulsed, with the pulse duration typically from few nanoseconds to tens of nanoseconds. The most efficient are self-terminating lasers on atom transitions, particularly yellow and green copper vapor laser and red gold vapor laser. Lasers on ion self-terminating transitions, about two of which I will talk in this presentation, are less efficient and more difficult to pump, which is partly associated with the necessity to operate at higher pulse repetition frequencies when active medium is highly ionized. Generally, for pumping self-terminating lasers, thyratrons with magnetic compression assistance or closing solid-state switches are used with typical voltage pulse age on the gas discharge tube of tenths of nanoseconds. In order to increase lasing efficiency and average output power, switches that allows to achieve higher voltage rise time on the laser at high pulse repetition frequencies were applied. So let's consider some examples of copper vapor laser pumping with such switches. In this work, in order to increase output laser power, average output power, COS diodes were used, and as a result, an increase in output in the average output power of 20% was achieved. In another work, by the means of step recovery diodes, also increase in the efficiency and the output power of commercially available copper vapor lasers were achieved. So, except these two works, there is one more. For example, here the thyratron causing gas discharge switch was used. As can be seen from the figure, which was taken from this work, in the burst operation mode, application of such a switch allowed to improve optimum laser pulse repetition frequency. In comparison with the case when thyratron was used. So when using with smaller operating capacitance and at high laser buffer gas pressure, even better characteristics demonstrated here were achieved. But despite such positive effects on laser characteristics, there are also some few disadvantages. First, it is rather high self-capacitance of the switch. For example, thyratron similar to one which was used in this work has a capacitance of about 50 picofarad. Another one disadvantage concerns the operation at the higher frequencies. I mean, tens of kilohertz. With the increase in frequency time, time interval between the moment when the high voltage is applied to the switch and the switch breaks down decreases. So you should use faster primary switch, or another option is to decrease switch operating gas pressure in order to maintain delay time the same. Decreasing pressure increases switching time and energy losses in the switch. All this prevents to achieve ultimate parameters of self-terminating lasers. So let's now consider another type of the switch, which was studied in this work, and as we suggest, is more appropriate for self-terminated laser pumping. This switch constructed from the is constructed from the capillary part and cathode region. In our experiments, a capillary of rectangular cross-section with dimensions of 10 to 0.3 millimeters and the length of 35 millimeters was used. As you can see, switch has additional electrodes, grid electrodes, in order to create plasma in the cathode region. This is done before the main pulse is applied to the switch. And it is important, it is especially important at low frequencies when electron concentration in the cathode region is lower. Also, as you can see, capillary has a metal shield around its outer surface, which has a great influence on the delay time. And the device is filled with helium, usually which has pressure few torrs. Electrical circuit also is demonstrated here, in which experiments were carried out. So the rather long, about 20 nanoseconds pulse from the generator is applied to the is charged in working capacitance, and then after some time switch breaks down. So here the typical oscillograms of current on through the load and voltage on the switch is demonstrated. In this figure, you can see the effect of brightization pulses, which is applied to the grid's electrode. 1 microsecond before the main pulse. So with the increase in the brightization pulse, the initial losses in the switch decreases. Okay, now let's move to the part concerning laser. So here the gas discharge tube of a laser is demonstrated. The experiments were carried out with barium vapor laser. The simplified energy wealth diagram is presented here. Except two ion laser transitions in barium, there is also well-known atom transitions in the near infrared region. And so it was possible to simultaneously observe ion and Wasing on ion and atom transitions. So here is here are waveforms of voltage on the tube, current through it, and pulses and laser pulses on ion transition and atom transition. All experiments was carried out with laser emission that has wavelengths of 640 nanometers. The generation on this line wasn't observed, presumably because of the high thermal population of the lower wasing state. All experiments were carried out in the burst operation mode when energy of laser pulses are in the constant mode. So here you can see evolution of the energy pulsing during the burst. It is here n is the number of the pulse in the burst. The frequency of the bursts was 1 Hertz, and the frequency for pulses in the bursts varied from few kilohertz to up to more than 100 kilohertz. So additional heating element to which was placed outside the tube was used to create barium vapor. Here, the main results of the work is demonstrated for the two temperatures. You can see comparison of laser pumping in two different circuits. In the first circuit, in the first electrical circuit, a solid state generator with further magnetic pulse compression was used, and the voltage, the output voltage pulse on the tube has 30 nanoseconds age. In the second electrical circuit, as that was presented earlier, Eptron was used, and it allowed to rise voltage on the tube for less than 2 nanoseconds. So here we can see that in case of Eptron, energy of the laser pulse is much higher, and the optimum pulse repetition frequency is also raised. So Here are another results presented. With increase in here we see the optimum buffer pressure for helium, which was used in the ways except the barium pressure. And another figure demonstrates the influence of hydrogen admixtures. So it is a well-known fact that in case of atom vapor lattices, particularly copper vapor laser, addition of hydrogen to the buffer gas improves laser output characteristics. But for ion self-terminating lasers, this effect hasn't been introduced yet. So here we see actually the effect of hydrogen admixture on the example of barium ion laser. This curve demonstrates pure buffer gas, and in this case we added some admixture of hydrogen, and as a result the optimum pulse repetition frequency and average output pulse increases. So let's introduce some preliminary results of the study of the mercury vapor laser study. So some advantages of the mercury vapor laser are its rather low working temperature, so it is easier to construct gas discharge tubes. Its level structure is similar to the copper, which is the most powerful atom self-terminating atom laser, and it has a rather long lifetime of laser transitions, about more than 300 nanoseconds, which is an order of magnitude higher than in barium vapor. So here the typical histograms are presented. The duration of the latent pulse is much higher than in case of barium laser, and this laser starts to work at higher pulse repetition frequency. So here presents the energy of second and third pulses in the burst. This is a preliminary studies, so to achieve best results, we need to improve our preliminary our primary generator. So conclusions are as follows. Characteristics of lasers on self-terminating transitions of barium and mercury ions were studied. Application of high voltage pulses generator based on electron allows to improve laser characteristic of barium ion laser in comparison with conventional generators. And for the first time, for laser on self-terminating ion transitions, the positive effect of hydrogen admixture to the buffer gas on output power at optimal pulse repetition frequency was demonstrated. And the last one is superlinear increase in laser energy of the pulse repetition frequency more than 100 kilohertz was obtained on the mercury ion transitions. Thank you for your attention.
Thank you, Maxim. Questions, please, dear colleague. Question. Dear Maxim, do you see a question?
Yes, I see.
Mm-hmm.
Could you briefly propose the relations between the switch characteristics and output? As I can understand questions, the question to achieve higher average power, average weight and power, and optimum operation frequency of the laser. It is preferable to use switches that allows to that are more faster, especially that are more faster and can operate at high pulse repetition frequencies. So from this figure, we can definitely see it.
Okay. Ivan Yegorov, do you agree? Okay. Another questions, please. I don't see questions. Dear Maxim, thank you again for. Oh, no. Sorry. Another questions.
Faster means faster. It depends to what degree. For these lasers, maybe 1 nanosecond is enough, but high pulse repetition frequency is needed, and there are only a few switches maybe that can operate with such parameters. What is limitation? Limitation is as follows: when we increase the frequency, the resistance of the laser tube is lowered, and so the pulse, so the voltage on the tube decreases. If it is not, if the leading edge of the voltage pulse is not short enough. So as the voltage on the tube increases, the optimum electron energy decreases, and laser output parameters becomes poor.
Mm-hmm. Okay. Okay. Another questions, please. No questions. I don't see. Maxim, thank you again for your talk. And
Thank you.
Okay. It is finished. Thank you all for participating. And